So first, you're going to get into your new groups, and you are going to you're going to use your laptops and find the definitions of all of these different characteristics of a simple harmonic motion. Period is something we've seen before because we talked about the period in universal gravitational rotation, or gravitational motion, rather. There's a relationship between period and frequency. For those of you who did the reading, you know what that equation is. So you're going to need that for our worksheet today. But the first setup, you're going to see it up here. Let me move my camera. Our first setup is going to be focused on the simple harmonic motion of a spring. Your springs are going to have a weight on them, and we've attached these flat surfaces to the end of it so that your motion sensor can read the position as it goes up and down. So you want to be really careful about making sure it's right above, making sure that your card is fairly flat, and then you're going to start getting it in simple harmonic motion. Now, this isn't a perfect scenario because we're going to lose some energy. The spring is going to lose energy as it stretches and compresses. It's going to develop some heat. So you're going to notice from your graph, you're going to print your graphs out, and this is important. Print your graph to room 306 because Miss McGarry's doing a similar lab in our class, and then we won't be able to figure out whose graph is whose if you don't print it to the right room. So you're printing out this graph. You want to make sure that you attach it to this lab to get your stamp. And I want to make sure that everyone does finish this lab at the end of the period. In your laptop, there is a file for Pasco Capstone called SHM Capstone. It should have a position time graph set up for you in order to graph it. Let me actually just open it up because when you graph your cycle, first of all, this is what you think it's going to look like. So you're going to do a educated guess of what the position time graph would look like, and then you're going to actually graph it. When you graph it on Pasco Capstone, there's this highlighter button where you've got like this little yellow highlighter. I want to make sure that you highlight a section of the graph that looks pretty and zoom into it because you can analyze the graph better if it's zoomed in rather than a tiny little graph right there. Okay? So my tech managers, and I'm going to show you what roles you play, is going to be in charge of making sure that everyone in the group gets a nice, beautiful, zoomed-in graph. And then from there, you're going to analyze what a period of that graph is, what the equilibrium line looks like, the amplitude, and then think about the speed, the energy, kinetic and gravitational, in the motion of a pendulum. So we're going to tie in some of the energy concepts that we learned from the previous unit. The next lab you're going to do, and you're going to actually calculate those so you can use points on your graph. You could use rulers. I have a bunch of rulers here to actually calculate your period, your frequency. And then we're going to get into this simulation, which will give us an ideal situation where we don't lose energy and everything stays consistent. I have this in Canvas. The link to the simulation is right here. And so your tech manager is going to walk through this simulation under the lab tab. And if you are under the lab tab, your period timer is going to be able to calculate your period. So that's the section number 2. There are 3 characteristics about a simple harmonic motion that you're going to analyze. So if you're analyzing amplitude, then you want to keep your length and your mass consistent. To calculate your period, you just click your timer and it'll stop as soon as one full up, back, and center cycle occurs. When you're changing the length, you can change the length this way but you need to keep the amplitude consistent every time that you change your length. So only one characteristic changes. Same thing with mass. If you change your mass, keep your amplitude and your length the same. Okay, after that, you're going to use the knowledge you gained from these two labs to answer the next few questions. And if you look at the next question, which is the graph right above question number 4, you get this crazy looking graph that is related to something called a double pendulum. So a double pendulum is a pendulum that doesn't just swing back and forth, but it has another pendulum within it that makes it move what appears to be sporadically, but there's actually a cycle there. So I want you to analyze that cycle just graphically. You're going to analyze the cycle using data points as well. So in the very back page, you've got a long and short pendulum. You're going to add those two values together to get the data for the double pendulum. And then you're going to analyze the data to answer the following questions here. And then last but not least, an analysis question, which is experimental design, just like what we've done in the last quiz or the last test. So make sure that you do complete all of this by the end of class. I do want your cell phones put away. I realize some of you started working on your homework, but there are important concepts for this lab that I want to make sure you did correctly. A lot of vocabulary, like I said, in this unit that are important, more so than calculations. So you want to understand the concepts, do the readings, etc., etc. Okay, there were a lot of things here that you had to mark in your specific graph. So for this lab, you had to include an equilibrium. The equilibrium is not the zero position. Where is the equilibrium? Any thoughts? Where did you put your equilibrium in your graph, Danny? Right between your 2 points. Now your graph might have decreased each time, but the equilibrium should have stayed the same. What about the amplitude? What would be my amplitude in this graph? Any thoughts for this one? How did you label your amplitude? Wilder.
I did the first peak because I figured that would be
the first peak, not all the way down to the bottom, but from the first peak down to equilibrium. This is your amplitude. Ideally, it would be the same from equilibrium to the trough. We call these bottom points troughs. They should be the same in value, but like I said, we lost energy over time. But our amplitude is from crest to equilibrium or equilibrium to trough. They should be about the same. The, what was the other one? The period or the wavelength. How did you measure the period or the wavelength for these? The time for one cycle. Kaya.
We went from the middle highest point and to the next peak.
The crest
Yeah.
to the next crest. So think about the vocabulary I'm using. You can also go trough to trough, or you can go from equilibrium up, down, and back to equilibrium. They should be the same distance. So this is what we call a period. Remember from universal gravitation, it's a capital T that represents the time for one cycle. And you can measure it many different ways. You use the method that is most convenient for the position of your graph. Some of you have just a few waves, some of you have more, so you want to know all different ways of measuring your period. Period is the time, wavelength is the distance. And it's represented by this symbol called lambda. So They represent the same value on your graph, but one is time, one is distance. Any thoughts on maximum velocity? Where do I have maximum velocity on this graph? Where is it its highest speed, Greta? Right at equilibrium. This is max velocity, which also means it's max kinetic energy. What about max gravitational potential energy? Where do I have the highest gravitational potential energy? Anya? At the top, because it's the highest height. And what about maximum elastic potential energy? Where's the maximum elastic potential energy? Was that part of your questions? No? What do you think? Where would be the maximum elastic potential energy? Because it is an elastic, right? It's a spring. Anya, where would it be? At the bottom. So this is max EPE. All right. So I think we've identified all the different ones. Make sure that you identified them correctly in your own. We've got amplitude, fastest speed, gravitational, elastic, and kinetic. Where's the lowest speed? I forgot to include that. Where would it have the lowest speed? Sebastian? At the bottom, it would have 0 velocity. Anywhere else? Kaya?
The crest.
At the top, at the crest, good. So, anytime it's changing direction, it stops for a moment, starts speeding up at equilibrium, it's at its maximum speed, and then it starts slowing down because of gravity. Then it stops again, speeds up, equilibrium, then slows down. So that constant speeding up and slowing down gives you the max velocity at equilibrium, minimum velocity or 0 velocity, top and bottom. The last thing I want to talk about is your pendulums, the ones that swing back and forth. When they swing back and forth, you tested length, you tested mass, you tested amplitude. What gave the biggest change of your period, the time for one cycle? What characteristic gave the biggest change? Anya? What was it? The length. The longer it was, the more time it took to make one cycle. Did mass affect it at all? Not even a little bit. The bigger your mass, just like with gravity, we did a demonstration where I dropped a book and a piece of paper. They fell at the same time, as long as there was no air resistance. It's the same with the swing of a pendulum or the bounce of an elastic cord. Your mass does not affect the rate in which it bounces. It might have more energy because of the mass, but it doesn't affect the period. All right. The hardest problem was this double pendulum. It's just giving you a little bit more complex of a method to test your understanding of one full cycle. So when you're measuring these, you have to look where it does 2 upward motions and 2 downward motions before it starts repeating. What value did you get for the period of this pendulum, this funny looking pendulum? 6. The thing you want to think about is it starts at 5 seconds, it does 2 up bounces, 2 down bounces, and then it stops at 6.5. The time difference between 0.5 and 6.5 is 6 seconds. And then in the back, when you test the hypothesis, you just want to make sure that when you add the 2 heights together, that it matches the pattern that she got from a graphical point of view. Does it match? Yes or no? What do you think? It should. You should see 2 upward motions, 2 downward motions, and back to center. Good job, everyone. Don't forget the reading, the homework. The answer key will be up if you have any questions.